Don't you love it when technology fails? They did 15 minutes before class. I was preparing all the stuff. And long story short, I'm sitting here debating. Do I bother telling them? Do I bother telling them? Because it might all work out, but I'm not optimistic and I'm pretty ticked. Turning point, the clicker stuff. There's an update available. You need to do this. So I do. And now it doesn't work at all. And long story short, I call up customer support and they say, basically it says, my operating system's too old. We don't support that. You need this. I'm like, well, I can't run that on here. It's like, wait, I've been running this for about the last year. I installed this last semester. I'm halfway through a semester. And he wouldn't believe me. It's like, that's impossible, sir. We've never had a version that did it. Well, I don't know what to tell you. Anyway, I got to call out to our representative, but if that's the case, then So all the clicker questions I had for you, we obviously won't be actually doing them, but maybe I'll just ask you what they are. We'll do it old school. Okay, I'll feel better once we start talking about relativity. I wanted to, before I open up questions to you guys, the last thing was the E equals mc squared. Energy is proportional to mass. And the proportionality constant is c squared. So, of course, that looks funny. We're used to seeing it as that. And this one, I have no cool way, the way it comes about off of the two postulates. They throw it in this chapter because this is what Einstein came up with his special theory of relativity. But the bottom line is, you know how space and time are related? It's like you can't separate them anymore. We're used to dealing with space and we think it's fixed, and we think time is, it just flows along. But somehow they're interrelated, and space, you've heard this, space can get warped. That's the general relativity. But the special relativity, we now have this space-time. Both of them are relative. Time is relative, so can space. Lengths can contract, and time can dilate. Seem like it's running more slowly, depending on which reference frame you're in. Well, likewise, just like all of that, Einstein said that energy and matter are related. You take a mass here, made up of matter. Well, it's like it's congealed energy. It's stored in that. Most people, I would say, when they see this, think of something with nuclear power and whatnot. Fission and fusion is where I find it the most conspicuous. You've at least heard of fission and fusion? Fission is when you split the atom and it goes into two smaller elements and energy is released. And you can make bombs and power things. Fusion is when you take two lighter elements and fuse them together, run them together. It takes energy to do both, but you can get a whole lot of energy out also. It's that idea that they're connected. You can take matter and split it and release energy. And what I find interesting is, it's uranium. You got an isotope of uranium that can fission. It has so much matter. It has a certain mass. You can weigh it, and they've done this. And then fissions. You can weigh what's left. And it's slightly less than what you started with. Well, where did the matter go? Where did mass go? It was converted to energy. Yeah. Yeah, nuclear bombs are essentially that. Fission and fusion. Mostly fission. Fusion, you take two lighter particles and ram them together and you get energy out. But again, the masses don't always add up the way you think it would. Basically, you think if you're taking several constituent parts and you weigh them all and add it up, you should get what you have once they're together. Or vice versa. You weigh it and then they split all up and then you weigh these. They should be the same. Basically, what Einstein discovered was that, nope. Matter can be converted to energy, and energy can be converted to matter. And so they don't matter itself isn't always conserved, and energy isn't, but the two are one and the same. Have you guys heard of antiparticles? We're not covering this, but like, raise your hand if you have. Oh, less of you than I thought. Antimatter, yes, yes. Oh, still less of you than I thought. Well, basically, it's like you have an electron. It has a certain size and shape and charge. And then there's something that's antiparticle, which is antimatter, called a positron. Basically, they're exactly identical, except this one's positively charged and this one's negatively charged. We never, hardly ever see the positron. We deal with electrons because it's antimatter. What's cool is if they come together, they can annihilate each other, and it's like they disappear. There's no more matter. But they release energy. They can convert into pure energy. And seemingly spontaneously, this energy could just all of a sudden, boom, and now you have a matter and an antimatter particle. So we've observed this. Another way this might, people like to think of it is chemical reactions. You know, you have a match. We could weigh this. You have a chemical reaction, obviously. I think they're just heat sensors instead of smoke anyway. But technically, this weighs slightly less. If I put any scale I have, wouldn't be able to detect it. But if we could measure it precise enough, some of its matter was converted into energy. And that doesn't seem too far-fetched, does it? You can probably believe me on that one. How many of you read the section in the chapter on this? A couple of you. Oh. Your test is next class. It says here, chapter 35, the part on E equals mc squared. I like one thing he says, so I was going to refer to it. And I should have put a post-it note right next to it. Let me find the right paragraph. There it is. This equation is not restricted to chemical and nuclear reactions. A change in energy of any object at rest is accompanied by a change in its mass. So you could look at a filament in a light bulb. When it's energized with electricity and lit up, it actually would weigh a little bit more because you have its normal mass that we're used to, but that energy. And since they're one and the same, it would actually have more matter. A hot cup of tea has more mass than the same cup of tea when cold. Now, when all else is the same. Because there's more energy in the hot tea than the cold tea. So there's actually more mass there. If you do work to force things together, we haven't got to electricity yet, but electrons, they repel each other because they're all the same charge. It would take energy then on my part. I'd have to do work, exert a force over a distance, to cram them all into a certain space. They would now store energy, a type of potential energy. And they would actually weigh more than if they were spread apart. Just some examples to emphasize this interplay between mass and energy. And then the very, very last thing, which we've essentially talked about, but I haven't referred to the name, is the correspondence principle at the very end of the chapter. That's basically what we've been saying all along. All of this has to make sense with what we already knew, which is why the special theory of relativity works at all speeds. It doesn't disagree. That's the correspondence principle in essence. You don't come up with something new that goes against everything that does make sense. It just usually extends it. Remember I said Newtonian physics works for us at these slow speeds, but it breaks down when you start going fast. So now we use the special theory of relativity when you're going that fast. But it also works down here. We just don't need to use it, generally. All right, questions about anything, but this relativity stuff, what do you guys, how do you feel about it? Yeah. Yeah. When you're going faster, volumes can change. That's because lengths can contract. So if I could run, near the speed of light, what would you observe about me? Yeah, my lengths would contract. And in which direction? I'm going this way. Yeah, in this direction, because I'm moving in this direction. So you would see me get smaller this way. So my volume would change too. Good. Anything else bothering people? I'm sure you stay up late at night thinking about this stuff, right?
So there was a question on the homework that said if you're traveling away from Earth in a ship,
Okay. Traveling away from Earth in a spaceship.
and you're monitoring your pulse.
Oh yeah, and you're on the spaceship.
Yeah.
And you're monitoring your pulse. Yeah. It's just a fancy way, and you could be looking at your watch. It's just something with a time interval. Yeah.
I was just wondering, I think it's because it said what would the person in that, what would you observe with your pulse?
Let's do both cases. All right, you're on the spaceship traveling near the speed of light relative to Earth. And you're looking at your clock, or timing. You get a certain thing. Compared to when you checked it at Earth, that's what it is. You have to have some reference point, I think is how the question asked. We're all here at rest. You do your pulse and you get something. Let's just for convenience say, it's 1 second. Every second we get a beat. If we hop on the ship and cruise around now and do it again, how will things be different? Yeah, it would stay the same. Why? Exactly, very good. It's because I'm at rest with respect to that frame of reference. We're moving together. There's no relative motion between me and my clock, me and my pulse. So yeah, you don't notice a difference. Time still clicks by for you the same way it always has. Lengths wouldn't contract either in that frame of reference to you because you're in that frame of reference, moving with it. It's at rest with respect to you. However, what does somebody back on Earth still see? So in this frame of reference, normal. That frame of reference, normal. But if I'm here looking at that one, what do I notice? Yeah, time seems to slow down for that person from my frame of reference. So I would observe the person on the spaceship's clock to be running more slowly. Time's stretching out. And his heartbeat would be less often, maybe every 2 seconds. Thus, he would seem to be aging more slowly than me. Go ahead. I see the wheels spinning there. No, it's not because they're getting closer to the speed of light. It's fundamentally because there's relative motion between our two frames of reference, period. And he could be going 50% the speed of light and not changing. He's not going any faster, so he's not accelerating. Then he'd be in a non-inertial frame of reference, and we're not covering that. That's general relativity. But just because there's relative motion between the ship's frame of reference and our frame of reference on Earth. So I would observe them, their time to be running more slowly, and distances to be contracted. Okay, now we're on the spaceship looking back at you guys on Earth. What do I notice from the ship? That their pulse is getting faster? Slower. Okay, at least the consensus is it's not the same. Good. Because we're in different frames of reference and we're moving with respect to each other. So yeah, it's got to be different. But yeah, does it speed up because we've switched? This way it's slowed down. So yeah, if you switch reference frames, you might want to think, it's the other way around. But no, it's actually slower. Again, because from the ship's frame of reference, it looks like the Earth is going that way at 50% the speed of light. You know, if you blocked and, you know, covered the windows and everything, how would you know whether you're moving versus that moving? It doesn't matter. It's all relative. Again, just because there's a relative motion between the two frames of reference, from this frame of reference, I see that one having time dilation and lengths contracted. This is the crux of the twin paradox, too. That's why it seems to be a paradox. How can I see time going slower over there, and this person see time going slower over there? Who's right? They're both right. That's the special theory of relativity in their frames of reference. And it's because they are in different frames of reference with relative motion between them. Normal, weird. Normal, weird. Now, if they come back together, they're going to be in the same frame of reference, right? Let's say the ship comes back to Earth. Are they going to agree? Well, what will be different? Their ages. Now, one of them, they both thought the other one was staying younger than they were, right? But if they get back together, they both, we've already discussed this, the one that went on the trip will be the younger one. And the key here is, now that they're back in the same reference frame, at rest with respect to each other and everything, they'll both agree on that. The one that was on the ship aged less. It'll be obvious. And the reason that happened was because this one actually changed frames of reference when they accelerated and turned around and accelerated again. General relativity. But while they're apart, yeah, it seems to be a paradox. Does that make sense now? Yeah, Glenn. Okay, so we stay put. My twin, I don't have a twin. My sister flies off to Alpha Centauri and then gets on Alpha Centauri. So in that sense, once she stops again and is at rest, let's just say for argument's sake, we're both at rest now, yeah, she would seem younger because she was the one that moved. Had to accelerate and decelerate. Now, if I come join her, now I'm moving. And when I get to her, that made me age less. And if it's the same exact trip, then she just did it first, I did it later. Now when I get to her, we'll be the same age again. Because while she stays put, she'll age more. While I'm traveling, I age less. And so I kind of catch back up with her youthfulness, if that makes sense. If you had the same trip. Which brings me to a point I want to mention up too. It seems impossible sometimes. You know, let's say it takes 70 years to get somewhere at the speed of light. Something 70 light years away. That's how long it would take light to travel there, 70 years. So it kind of represents a distance of 70 light years. Anyway, from this frame of reference, it would take 70 of my years to get there. That's what I think. I'll be dead. That's no fun. Don't sign me up. However, it is possible. Because if I get on the ship, now relative to everybody here on Earth where it seemed to take 70 years, time slows down for that person. They got more time to get there. Or if you're on the ship, things seem normal to you, but back here on Earth, lengths contract. You have less distance to travel. So you can make it there, you could make it there in your lifetime once you change reference frames. It's just if you stay in this one, 70 years click by. But if you get on the ship, you age more slowly relative to us here. So you can make it. It wouldn't take 70 years for you on the ship. To you in that frame, it'd take a lot less, depending on how fast you're going. That's interesting, I find. There was. Oh. Yeah, that was a theoretical question, if you could do that. You can email me with some justifications if you want. But yeah, technologically, we aren't able to do any of this stuff yet. Yeah. Mainly because of that momentum thing. The faster and faster you go, the Lorentz factor goes up. And the momentum goes up by that amount. It's going to take more and more momentum the faster and faster you go. You have to change your momentum. And how do you get a change in momentum? You apply a force for a certain amount of time. It's going to require more and more force, more and more energy. And technologically, we can't do that yet to go fast enough. Good. What else? Anything?
What percent of the speed of light are spaceships going right now?
You mean like the satellites?
Or like what's the fastest? If we were to...
Oh, the fastest possible? I don't know. You can, what is it? Is it 8 kilometers a second? An hour. No, kilometers a second. It said in chapter 10 what the escape velocity of the Earth is. That's kind of around there. And I forgot what it is off the top of my head. But point is, you can look it up. It's fast, but relative to the speed of light, which is 3 times 10 to the 8th meters per second, is that 300,000 million meters a second? That's really fast. So we're not relativistic yet at all. Enough we can note the difference in nanoseconds, you know. But yeah, we're not even close. Us. Some particles and things we've seen can go near the speed of light, and we can detect that. And the times it takes them to do things, we use as tests for this theory of relativity, and they've all matched up. For example, cosmic rays. This is one of the first tests, briefly. Basically, cosmic rays, there's these radioactive particles called muons that form in our upper atmosphere, and they come down to the Earth for us to detect them. Well, we've since been able to figure out their half-life. That's how long they live. And their half-life is less time than it takes for them to get from up there to down here, to cover that distance. From our frame of reference, to travel that far in the amount of time before they disappear, change, it seems impossible. Yet, we still detect them down here. The rate we detect here, we know how many we started with, we know how many we ended with. Way more make it down here than we think should work. So how do they reconcile it? The theory of relativity. If you're in that particles frame of reference going that fast, you have less distance to travel from our perspective, and you have more time to do it. And the numbers match exactly. So we use the theory of relativity when we're dealing with fast particles in their frame of reference. Good questions. What else? About anything? All right, take a breather. I'll do a demo. Think of some. I like this one for reviewing. I call this the high road, the top ramp, and the low road. I have 2 spheres. They're identical. They say I'm going to put them on here. They're going to roll. I guess I should see if we're level. And the first question I want to ask is, who's going to get over here first? Or will they tie? A little bit of gravity there, no problem. So I'm going to release them at the same time from over here. Who will make it over here first? See, this is great. I would use a clicker if it was working. We'll do it old school. Who thinks the high road? This one will get there first. 1, 2 takers. Low road? So all the rest of you think it's a tie? Most of you think it's a tie. Yes, we will. Want a drum roll? The low road. So somebody tell me, what were you thinking with tie?
I was thinking when it goes down and then come back up, it would kind of even out when it was coming back up.
It goes down, and when it comes back up, it'll compensate for itself. So here it'll be going faster, but then it slows down, so they'll still tie. All right. Glenn, you want to add to that? Since your hand went up? He's on. Anybody else want to add to that? Same thing? You agreed? Okay. Yeah. If they were to tie, it'd have to slow up even more? Is that what you're getting at? Oh, yeah. Well, let's talk through it more and see if you still have that question. What's the same here? Say again? Potential energy. Good. Also, their velocities. Yeah, they start out with the same energy. Well, what's going on when they get to the middle part? I guess I get ahead of myself. What's the same here? Their velocity, thus their kinetic energy, and potential. They're the same height. Do they have a little less potential than they had up here? But they still have some potential relative to, if we call this the bottom, you know. All right, so they're going the same speed. So it really starts happening here. What does this one do? It's converting potential energy to kinetic energy. And back to our first section, first unit, gravity accelerates it down. So it changes its velocity and it's going faster. So watch the speeds of the two balls when they're in this section. Could you see that this one compared to this one? It was going faster for this whole time. If you go faster, then you cover more distance in the same amount of time. So it gets here before this one does. I think I haven't confused any of you yet, right? All right. So now it comes back up. What happens to its velocity? Slows back down because it's decelerating. Kinetic energy is converted into potential. And this potential is the same as it was over here, right? It should be, ideally, right? Barring friction. And now has the same potential energy as this guy. So why did it not tie? Oh, is this one going the same speed as this one? Ooh, let's try that. Let's see, if I let go, so if I, see if I can time it. I have to let go of this one first, because he's going to take a little longer, right? Let's see if I can do that. And we're going to observe the relative speeds when they get to here. That's what you're asking, right? What do you think? Yeah, it looked about the same to me, too. Yes, because they have the same energy again. The potential is the same, so they should have the same kinetic there as they had here, ideally. They're now going the same speed. They have the same velocity. So, how do their velocities compare here? Who's faster? Bottom one. How about here? It's still the bottom one. This bottom one's going faster than the top one from this point to this point. So yeah, you're right, it does slow back down, but it's been going fast that whole time. That's why it gets ahead. So that one actually wins the race, but they both end with the exact same energy they started with. They both end with the same exact kinetic energy. They're both going the same speed when they finish. But the low road gets there quicker because most of the trip it was going faster. Yeah. Yeah, if this was a test question, yeah, that's what I'd hope you'd do, is utilize conservation of energy and velocities and accelerations to justify why it did that. Is it clear to people now, or do you want a little more? I think it kind of brings all that in to one thing nicely. How do their energies compare here? How does the high road's total energy compare to the low road's total energy? Yes, there's more potential energy here than here. Correct. What else? But this one has less kinetic than that one. The total, though, should be the same. The total energy here is the same as the total energy here. It's just now this one's in kinetic, which is why it's going faster. And this one, it's more in potential, which is why it's going slower. But the total energy is the same. How do their momenta compare right at these points? Since they're the same mass times velocity, this one's going faster. So yeah, at this point, this one has more momentum than this one. They end with the same momentum when they're going the same speed. But they do that at different times. So yeah, there's several things, between times and velocities and momentums and potential energy and kinetic energy. I know it can seem kind of sometimes, but you know what they all are. You just think it through. And things like this, I hope you can see, are pretty simple once you can pick out the things. Of course, I know it's easier when I'm sitting here talking about it. But all right. Any questions? Other questions about this? All right. Do you guys think of any other questions? Projectile motion, yeah. You got something specific in mind?
I was just thinking about, I'm getting a little confused on, I remember we did the example, the demo class with the bullet, wires.
The wood bullet shooting the monkey?
Yeah. I'm just getting a little confused on, I guess, how how it hits the monkey, I guess.
And that velocity is initially 0. Okay. So as soon as this comes out, and with this velocity, he falls. So this one, if I just look at horizontal, because you have to separate two-dimensional problems into two one-dimensional problems. So let's just see what's going on horizontally. The easy one. What's the monkey do horizontally? Nothing. Well, if you have this velocity, well, I don't know what it is. Let's say it's 10 meters per second. Then, in 1 second, it'll be 10 meters further. Over here. After another second, it'll be another. Not the scale, obviously. And so on, horizontally. So that doesn't change. Here, then here, then here, and then over there. But now let's look at vertically. What does the monkey do? Well, he's accelerating at g, which is 10 meters per second every second. So he'll be a little farther after that first second, a little farther the next one, and even farther the next one because he's picking up speed vertically. What's the acceleration of the bullet? Same. Accelerates at the same rate. So it's going to do the same thing vertically. You'll have one, I'll just make it easier to draw here. And down here. You with me so far? This is all good? So now you just reason them together. This one is moving horizontally at the same time it's moving vertically. So after that first second horizontally, it'll get to here and to there. after the second, it'll get over to here, and as if it fell from here, it'll go boom, boom, down to there. And the third second, it would be over here, right? One more, and as if it fell from that point down to there. So its actual path, whoops, will look like that. And they will both be in this part of space at the same time. And they hit.
So, like, when the bullet is traveling, it's maintaining its horizontal velocity.
Yeah.
That's why it's able to catch up with that.
Yeah, when the bullet's going, yeah. Why does it keep going at 10 meters per second horizontally? Is something pushing it? It's out of the gun, it's in the air. Yeah, the gun pushed it initially and accelerated it up to 10 meters per second, but then it left the gun. So why does it stay moving? Neglecting air resistance, you're right. The only force acting on the bullet is its weight due to the being accelerated down by gravity. And that's vertically. So that's why it starts accelerating downward. So why does it keep 10 meters per second horizontally? Inertia. Way back to Newton's first law. Things in motion want to stay in motion. We always kind of stop there. Things in motion want to stay in motion, and things at rest want to stay at rest, unless acted upon by some force in that direction. And nothing is acting on it horizontally. So it doesn't speed up, but it doesn't slow down. It just stays at 10 meters per second. So it maintains 10 meters per second horizontally while it's falling. They're completely independent of each other. Even though they happen together, we reason it through separately. So if I shot it at 20 meters per second, same exact thing happens, but both of them wouldn't have had as much time to fall as far, so they'd hit higher up. And if it was going more slowly, they would both have more time to fall before they hit. And even as we did, we tipped it. Right? We shot it, we aimed up. But the same thing applies. After 1 second, this will go up a little bit. You know this guy's trajectory will be something like that. This guy will fall straight, and they'll hit. But you can figure it out, just like we did up here. Horizontally, it gets to this point. As if it fell from here in 1 second, how far does it drop? That far. How far did it drop after 2 seconds? That far. Likewise, after whatever time this is, let's say it gets to here. How far would it have dropped from that spot? Right there. And so everything still exactly applies. Even if you shot down, it'd work. As long as you initially are aimed right at it. How about time in air? Let's see this. We did it, that one, they're both in the air the same amount of time. So we released them together. What if, we had the two spheres where I shot one horizontally and dropped the other one? Remember that? Who hit first? Same time. What if we changed something? What if we shot this one up instead of down? What if we shot it down instead of, let's do that one. What if we shot a ball below the horizon, that way? At the same time, we drop one.
Does the other one drop from the same spot?
Yeah, same spot. So it's like me throwing this one down when I drop this one at the same time. What'll happen? You think the one I throw down will hit first? Why? Because I'm throwing it down?
Yeah.
That's the non-physics answer.
Because just like the example with the monkey, if you aim the whole thing down, the monkey will be below where you're aiming at. So just like if you're aiming up, the monkey will be higher than it was before. And so if you bring it all down, it'll be below where you're shooting the gun from.
Yeah, it's like as if you turned off gravity, it would end up lower in the first place. Is that what you're getting at?
Yep.
Okay, who wants to add to that? I'd have to get it up to speed. So it would now have a horizontal velocity and a downward velocity initially.
So it already initially have like that downward velocity, and then on top of that, as soon as it leaves your hand, you grab it.
Yeah, they both explain it. If it already has an initial down velocity and it gets accelerated down, it's going to go down more quickly than the one that started with 0 velocity in the downward direction. Yes? So yes, it would get there first. Or look at it this way. The one I throw down will spend less time in the air than the one I drop. Because it's going faster vertically the whole time than the one I just dropped. Remember our shooting projectiles, 60 and 30 degrees? That was one set of pairs that added up to 90. 60 plus 30 is 90. You shot the 30-degree angle and it was like versus the 60 that went higher. But they landed in the same spot, essentially. Who spent longer in the air? The 60, because it had more of a vertical component. It was in the air longer. So again, the 60 might look like this. Let's see, this would be 45 because they're equal magnitude, up and over. So 60 is more up than over. So like this, right? Do you see what I'm doing? So here's the vertical component. So it's not, this determines how far it'll go that way. And it's not as great. But it's in the air longer because it's shot up higher. Versus 30. Now, this is larger, so it'll go further. But it's not in the air as long. So when the pair adds up to 90, they agree where they land. So like 15 and 75, or 40 and 50. They don't all go the same distance as those sets. But if they add up to 90, it works out that way, ideally. The one that's in the air longer, we saw 60 degrees, actually was what, maybe 6 or so inches less? Because air resistance slowed it down horizontally. Vertically also, but we weren't interested in how high it went. Other questions? Yeah. They do land in the same place, neglecting air resistance. So that's like the shoot it at 30 versus 60. I think there's a nice picture in your book, I think. But the 60 path is in the air longer. So if you shot these at the exact same time, who would hit the ground first? The 30 would get there first, but they would go the same distance. Again, distance and time and velocities, they don't always have to. They didn't get here at the same time, but when they did, they had gone the same distance and are at the same speed. So don't get confused just because one's the same as the other. And there's another example. If the kinetic energy is the same, say you got two objects, a heavy one and a light one. A heavy object and a light object that have exactly the same kinetic energy. What do you know about their velocities then? Well, if you have a big mass and a little mass, yeah, this will have to be going faster than that one if they have the same kinetic energy. Let's do this demo. A little bit about momentum and impulse review then. I have a sharpened pencil and an unsharpened pencil and some piece of plywood. I've clamped this one in here. I'm going to exert a force on them with this. It's going to push the two. I'll start with the sharpened. It's going to exert a force on the pencil for a certain amount of time. It's going to change its velocity. It's going to change its momentum. A change in momentum is called impulse. And impulse is the same as force times time. So I'm going to apply a force on this pencil for this amount of time. That will change its momentum from 0 to a lot of momentum. It accelerates it. That force changes its velocity from 0 to something fast. It gains kinetic energy. We take this stored energy in here and get this moving. It now has kinetic energy. Likewise, the exact same thing is going to happen to the unsharpened pencil. They're essentially the same mass. They're both going to start at 0. They're both going to get up to about the same speed and have the same momentum, so that's the same change in momentum. The same impulse was applied. They'll have the same kinetic energy when they come out of the tube. Then I'm going to ram both of them into the board to try to stop them. You ready? Let's do the first one. 1, 2, 3. And it sticks. I grew up in Kansas, so I'm familiar with tornadoes, and this happens all the time in tornadoes. I see things that should not be stuck in other things after the storms. I think some of my favorites, despite the sadness of it all, is a carpenter's level, one of those long ones, was wrapped around a tree. 2x4 in the side of a truck. A tennis shoe was stuck inside the siding of a house. Because basically they're going fast, and then all of a sudden this exerts an impulse on that to change its momentum to 0, to stop it. So given what you see here, what do you think the unsharpened pencil will do? Same? Worse? Just bounce off? Or maybe go through farther? There's only one thing different about the two pencils. One's sharpened and one's not. So you're saying the sharpened one might have a longer impact time? If that was true, let's reason it through. What does that tell us? They're going to have to receive the same change in momentum, right? Because they go from a certain momentum to 0. They're both getting stopped. And I'll make it. So they have the same impulse. Because that's the same thing. So force times time, that's what we're doing. So according to what you're saying, if the sharpened one takes more time, then, and the other one's the other way, it would feel more force. So based on you, this is the sharpened pencil, and this is the unsharpened.
Yeah.
So what do you expect the result to be if the unsharpened's hitting with more force? 1, 2, 3. Boo. You're correct, and that was supposed to happen. All I can think is maybe I've used that board too many times, or this is about empty. So I'll try it again here. But your explanation is correct. This one hits all at once. So it's a fast impact. The sharpened one acts like an airbag or a cushion, a crumple zone, and it does extend or lengthen the time of impact. So you feel less force. Hopefully this still has one more shot in it. 1, 2, 3. Oh, yeah. Much better. So same impulse, same change in momentum, but this one was in impact less time, so more force. Made it farther through, more damage. More time, less force. All right, if you think of other questions over the weekend, email me. Yeah. Oh, the test is procedure is the same as the first one. You can have a cheat sheet, a calculator. We'll take it in here, same format and style, 30 questions. Makeup option if you take it on the exam day. So just like the first one.